AI happens pretty fast. If you don't stop and look around once in a while, it might just pass you by.
Hello, and welcome back to The Reasoning Show. I'm your host, Brian Gracely, and today I have reason to believe that no matter how fast we can build new data centers or get permits to build new data centers or figure out new sources of electricity, that we're going to have to figure out ways to be much more efficient with the data centers that we're building, as well as how companies that are running data centers can go about getting efficiency out of the powers that they need. So we're going to dig into that and much more right after the break. Today's show is sponsored by Nasuni. There's a growing gap in AI right now between what's possible in theory and what successfully works at scale inside an enterprise. The difference comes down to unstructured file data. Many AI initiatives struggle because the file data they depend on is scattered, unstructured, and disconnected from where and how work actually happens. Nasuni changes that. It brings your unstructured file data into a single, secure foundation so AI, both generative and agentic, can access it with the context, governance, and performance it needs in production. Bring AI to where your unstructured data lives. See what it takes to activate your data for AI and request a demo at nasuni.com/AI. Today's show is sponsored by ShareGate. You're out of time. Copilot needs to be deployed ASAP, but your tenant really isn't ready for it. Years of data, permissions, and users lurk in its shadows, ready to be exposed by AI. ShareGate Protect sees it all, so you can find the exposure risks, fix them fast, and deploy AI with confidence. Microsoft 365 governance, they've got this. Learn more at sharegate.com/protect. And we're back. And today we're going to dive into something that, we've been thinking about quite a bit, and I know is sort of in the news quite a bit. It's being talked about quite a bit, but it may not be something that everybody is necessarily thinking about because it may not necessarily be the thing that you're responsible for. But ultimately, as we're seeing so much discussion about new AI models, new deployments of huge racks of GPUs, we're ultimately talking about deploying a lot of data centers, needing a lot of energy and power, both from the data centers themselves, as well as the electrical utilities and the grid and so forth. And today we're going to really dive into how that's evolving, how we're able to do that efficiently. And so excited to have Marissa Human, who is CTO at Utilidata. Marissa, thanks for being on the show. Great to have you here.
Thanks, Brian. Very happy to be here.
Yeah, no, I'm good. I'm excited to dig into this because this is a topic that we've kind of covered around the edges as we've seen announcements out there, but we've never really dug into how this is all happening, but more importantly, like, how are we going to get the math to work out with all this demand on the AI side and all this sort of potential on the energy side, whether it's in data centers or others. So excited to dig into that today. Before we get too far into everything that you guys are doing today, give me a little bit of your background, and then ultimately, what do you focus on these days at Utilidata?
Happy to. So I'm a physicist by training, but as the Chief Technology Officer at Utilidata, I really am more of a practicing systems engineer. Utilidata has 15 years of experience running power flow for utilities. We started by adding metrology or digital readings in substations and turned that into decision making on a real-time basis and started kind of that very first wave, 2012, 2014 of making substations more efficient. And then since then have evolved our technology to run at the edge of the grid and now running inside of data centers. I like to joke that the electrons are the same everywhere. They might be running through slightly different equipment and they might need slightly different conditioning in order to perform the work that we want them to perform. But fundamentally, the physics stays the same from the substation all the way down to a GPU that's doing a piece of math.
Yeah. And that's, I think what really interests me about what you guys did is that history of, you've worked with utilities for a long time. Obviously, they're always trying to get more efficient, moving into the data center space or evolving into the data center space. Like you said, same sort of problem, but the timeline, the sort of demands are, I would guess, very, very different. One of the things that you guys are doing that's very unique is bringing a sense of AI to how you go about that efficiency. Can you walk us through a little bit of both where you're providing capabilities to drive efficiencies, but also where the AI aspects come into play?
Yeah. Yeah, so I'll start again with kind of our historical product and then move into kind of where we are currently. AI, which we used to call just like data science or
Yeah.
machine learning, a decade ago, is really a matter of using the measurements that you're getting from a system to inform maybe kind of a black box model, a model based on just the observations, and then turn that into a prediction or a decision. And when we started doing this with substations, we did those models across very large areas and longer periods of time. And so those models, I would call them kind of central because you needed to have a wide variety of information coming into them. As we have evolved and have seen the complexity of the grid evolve, we moved those models out to the edge of the grid. And so when we talk about now AI as part of our power flow optimization, our power flow orchestration platform, it is running those AI models, so sense and model and then decide right at the edge of the grid, because that is where the most dynamic behavior happens. And that's true if, when our product is inside of a meter that's on the side of your house and it's looking at, the local transformer loading and it's looking at your EV charging in your garage. But it's also true in a data center when you're looking at rack level power flow dynamics. So how fast is the power ramping up at that rack? And what can you do to mitigate any of the negative effects of that change, that rapid change, on any of kind of the upstream equipment from there?
Yeah. I know most people are probably familiar with kind of the ebbs and flows that go on in a utility in terms of, you can imagine power is used quite a bit during the day, whether it's at the business or at the sort of residential level. You have times in the evening, for example, maybe when people are sleeping, you're not going to use as much. And we've all seen these sort of different pricing when things are at different levels. I think when we think about these new AI data centers, at least the discussion is always about they're running all the time kind of, as efficient, as sort of full capacity as possible. What do those two different worlds sort of look like from how you guys measure things, how you sense things, but also how you start thinking about driving efficiency for them?
Yeah. So first, I think there's kind of let me back up and provide a couple different definitions. Efficiency can be measured as like how easily can you turn a piece of power, a watt, into the workload you want. The other kind of efficiency, and the one that we focus on, is system utilization. So for the system you have already built, the poles, the wires, the transformers, et cetera, how efficiently can you transmit power through that in order to get that work done? The former, how efficiently can you operate your system from like a thermal perspective, is stuff we've dabbled in the past, but we really do focus now on what I would call capacity utilization or an efficient use of your built environment. The way we approach that with AI is to really use real-time measurements to determine where the flexibility is in the system. So on the power grid, you're right. There are times of day where the power peaks, where people are using more power. Over the course of the year, you might be in a winter peaking system. If you have a lot of electric driven heating. You might be in a summer peaking system if air conditioning is your bigger power concern. For data centers, it is less seasonal, but it's very workload driven. So The two big types of AI workloads that people are familiar with, training a model versus running the model in order to get an output, have very different profiles. So in a training workload, a large portion of the GPUs will be in sync, like they'll all be doing kind of the same thing at the same time. And at times that'll utilize the full power capacity, the full compute capacity of the data center, and then it might drop back down while it's doing some other activities. When we're doing inference or when we're getting stuff out of those models, it's very dynamic. So small numbers of GPUs will be used to run a particular workload, and they will also ramp up and ramp down. And so the notion that AI workloads are high and constant is probably a little bit of generalization. They do use a lot more power as a consumer than anything else we've seen on the grid. We're putting in gigawatt level data centers when your town next to it might not even consume, 500 megawatts. And so they are much bigger, but they're not that uniform. And as a technology company, we want to take advantage of that variability and turn that variability into flexibility. And that flexibility then translates to efficiency. So by having very, very tight observation and then tight control of that system, you can fit more power consumption in at the right times. And that can be done for both the data center, for their outcome, but it can also be done in conjunction with the grid.
I gotcha. So you guys, obviously you've got a history of doing this. You've got models that you've built, sort of this intelligence to do this, and then now you're beginning to work sort of directly with folks like NVIDIA. You're building some chip level capabilities or intelligence. Kind of give us a sense of what the Carmen platform, the one that you use to do all this, like how is it? What's it looking at, and what's it determining, and then how is it actually driving this efficiency? How much of it is sort of working backwards towards the utility, or how much of it is sort of, having to pass intelligence or something to the data center? Where does the efficiency sort of come from?
Yeah. So you're right. We worked with NVIDIA over the last 4 years on a compute module that is very small, so less than the size of a credit card, and can run full AI models. And we made it that small and specialized for power system optimization in order to be able to embed it into power flow equipment that is critical for both the grid and for the data center. So since it's the size of a credit card, we can put it into the meter, we can put it into power distribution equipment. So there's many places along the system where high resolution measurements. So we combine that compute with being able to sense the voltage and the current at 1 million times per second, which allows you to really see all of the full dynamics of the system. And we embed it at the edge because, again, that's where the most interesting behavior happens. And if you can turn the variability or the inconsistency at the edge into flexibility, then you can turn that into a more efficient system. So let me walk through an example of that that we are implementing in the data center. So the power infrastructure in the data center, which, by the way, mirrors the power infrastructure on the grid, includes parts of the power infrastructure that are just there for redundancy. They are there in case something fails. Now we can move power consumption over to these other lines, these other pieces of equipment. All of that is based on what I would call like 1960s thinking, which is we overbuild the system and we provide that redundancy, and we require zero human interaction with that in order for it to work. So it's a completely fail-safe system. Over the last 50 years, though, we have developed some other technologies and tools that allow us to treat that in a more dynamic manner. So what Utilidata brings to those systems is that very fast sense and control that allows you to operate in that redundant space. So we can take a built data center and be able to run it 30-50% higher than its original spec capacity, because we have the ability to manage the system in less time than it would take for you to flip the breaker in the system. So if you can use software-defined systems to optimize the power flow, you can reduce the amount of stranded capacity that's in the data center.
I gotcha. So if I'm sort of repeating that back to you. So for anybody who is listening, we've all sort of dealt with this, in which you build redundant systems for obvious reasons, for reliability reasons. But you sit there and you're like, we spend a lot of money on this stuff that doesn't do anything for the vast majority of the time. And you're like, it would be great if we could utilize it without losing but when an actual failure happens, I want to go over and switch things over. You guys, in essence, are like, hey, we're building in, we're sort of oversubscribing the system to a certain extent because you're using the repetitive or the redundant system, but you're fast enough to realize that if that failure happened, you can kind of get back on track or get back into the system that was supposed to be designed there without the system knowing you're doing that, in essence.
That's right. Yeah. Okay. So like very, very simply, the data centers are designed often they call it a 4 to make 3. So they put in 4 lines and they would say, we can lose one of those lines and operate the data center on 3.
Gotcha,
and we say, oh, well, you can have a 4 to make 4. except those rare times when you lose one line, and then we can back your load down to just run on those three, which solves one aspect of interconnecting new data centers. It does allow you to get more capacity out of the existing data centers. It means that like the investments that we've already made in the power lines and in the equipment could be extended further before we build the next one. But it also, the kind of underlying techniques of, again, like very fast sense and control also allow you to now play nicely with other types of grid dynamics or other types of power quality issues. So being able to expand how much you can get out of your data center is one part of it. And then the second part of it is let's also use that control system to create the flexibility and that efficiency that we need.
Gotcha. Now, so in that sort of 4-for-3 concept or 4-for-4 concept, the obvious thought would be like, okay, cool. I'm getting at least somewhere in the range of 25% more capacity out of it. Does that also have downstream effects on either helping, does that have any way of sort of helping compute in terms of either how fast it runs or how long it can last? Or you're sort of like, we just want to make sure you can run it, maybe even more capacity than you had planned for without challenge?
Primarily, it is being able to run more capacity than you originally spec'd. And certainly as the power density of the AI compute racks increases, so literally from one generation to the next, you can fit twice as much capacity into the same space. And so, as you evolve your fleet of compute in a space, you would want to be able to, continue to fill it up fully physically. And that means you also need to be able to manage that capacity. There are other pieces of this that I think are going to come into play. And I think if you've heard Jensen, NVIDIA CEO, talk about this, he'll say that there's probably X more capacity than we're currently using. So in the data centers, ranging from the yard, where you have all your power distribution equipment, all the way down to the GPUs. And it's really a matter of visibility. Can you see it? And then, can you do something about it? And that's that very tight control loop.
Now, are you usually, the services that you guys provide, is it typically to the utility provider, or is it typically to the carrier, or not to the carrier, to the sort of the data center owner, or are you oftentimes on sort of both sides of that, and there's a way that your intelligence could sort of be shared multi-directionally?
So today in the data center, we're very focused on helping the data center operator get that visibility and orchestration of their power. The utility has responsibility right up to the meter or the point of common coupling with the data center. Yeah. So today we're focused on what I would call behind the meter, and that is helping the data center operator understand what they can do around their capacity management inside of the data center. I do think, though, that information, when the utility has an API endpoint to accept it, would be very valuable for their system planning. So we're operating in that millisecond timeframe. The utility does not want to understand what's happening on, at that less than a second, but they would like projections about what's going to happen over the next 30 seconds, minute, 10 minutes, hour, 4 hours, et cetera. Like those are kind of the timescales that the utility would be able to manage their generation fleet or manage their power flow on the transmission level in order to both serve the data center and the rest of their customers.
Yeah. I have a question, and I don't know if this is something that you can answer, but as I'm thinking about your ability to essentially extend or to provide greater capacity without a whole lot of downside or limited downside. Right now, we're hearing all sorts of stories of there's all this pent up demand to build new data centers. They're trying to get built as fast as possible, but oftentimes there's bottlenecks in the systems, whether it's construction or availability of to generate energy. Does your ability to sort of make that 4-3 look like 4-4 help accelerate things, or are you still sort of bound by, well, we can't really allow that to kick in until it gets sort of final approval, and then you guys jump, the 4-3 is sort of the final approval. It's been inspected by a local regulatory, and then we sort of amplify that? Or are you finding as we're hearing about more data centers that kind of have to go faster than the utility could provide, do you guys help accelerate that in any way? Or am I kind of getting outside of what you provide?
No, I think you're hitting it right on the head. So kind of two ways to look at this. One is that for a hyperscaler, they have many sites that they're, both managing right now and they're building out. Our solution helps them get, 30, 50% more out of their existing sites.
Okay.
That's the fastest way for them
Yeah.
to get there and has the least amount of strain on the grid
Yep.
and their nearest neighbors to that data center. So that piece doesn't help them get approval for the next one faster, but it definitely helps them just get through the next bottleneck faster. And that is like at the heart of the company's kind of physics is really like, let's use the built environment to its fullest capacity. And, when we're talking about that for the utility grid, that's saying like, hey, the distribution system that is delivering power to your EV charger and your neighbor's EV charger, if we just offset you two by, a couple of hours, now we don't have to replace your transformer in order to service both of you. And the same thing applies inside the data center. So a little bit of management goes a long way to being able to use the existing capacity to serve more load. Yeah. And then on the other side, like actually permitting new spots, I think that our technology helps people rethink their capital allocation, their actual capacity investments. Because if you don't have to overbuild your system in order to deliver X amount of power, it costs less and it's a lower impact on the environment.
Sure. It makes sense. Is your customer base almost entirely, at least on the data center side, sort of hyperscalers and neoclouds, or are you also seeing, it seems to me like the technology would be valuable to, sort of a large enterprise who's saying, hey, I'm now having to put some GPUs in my data center. We weren't necessarily prepared for the uplift in how much, power it was going to take. Does that come into play, or are you guys still, are more or less just sort of like completely full in terms of keeping up with hyperscalers and neoclouds?
I would say the primary customer is the data center owner operator that really has management responsibility from power all the way through compute. So enterprise customers are that, even if they are like sometimes they're inside of a co-location facility, but they often have exclusive rights to, a pod or a set of the infrastructure. And so if they have management over that infrastructure, then they have the opportunity to get more out of that infrastructure than what they're currently doing. Okay,
that makes sense. One last question before I let you go. Anytime we talk about the grid, there's oftentimes at least an ancillary or side discussion about the grid's important for national security and national importance. You guys, do your systems get involved at all with the systems that are also looking at the stability of the grid, or thinking about it in terms of how do we keep this safe? Apply proper sort of redundancy and security around it, or is that typically a separate thing?
No, we are part of critical infrastructure. We are embedded distributed power flow management, and so that would be the same as if you had your central power flow management. And we take that very seriously. So from the point of manufacturing all the way through deployment, we have very tight control over the supply chain and the handling of that supply. So we are very confident when we deploy these AI computers that are managing power flow that they are running the code that we have designated them to run, and they're going to take the actions that we have permitted them to do. And then once they're on the system, we're very careful about how they're networked and how that data is accessed. And for the most part, keep these air gapped. So they talk to their local equipment, but they don't talk to the internet. They're not accessible from outside the system. Yeah. And as I said, we spent more than a decade on that and have a great deal of respect for how this whole system comes together. We're one part of it, but being good stewards of both the information and then the control actions it's part of our DNA.
Yeah. That came across. Yeah, it is one of these things that it's always interesting to see the companies that evolve from, like you said, systems that have been around for a while into sort of these faster moving places. And you do hope that they can bring that level of knowledge they had with them and then obviously evolve it with the innovation that happens. So, well, listen, Marissa, we've dug into some stuff. We've probably really just scratched the surface. I appreciate you taking the time to educate us a little bit on, how we're getting the amount of power that we need and sort of the demands that people are asking for. So with that, folks, I want to thank Marissa for her time. I want to thank her for her insights. Hopefully this has been useful to all of you. With that, though, I'm going to wrap it up, and we will talk to you next week.
Check us out online at reasoning.show for all things reasoning. And leave a 5-star review wherever you listen to the show.